Hey everybody, in this next video lesson we're going to begin talking about the different states of matter and how intermolecular forces affect each type. We're going to begin with solids. Solids, as you know, are substances that don't have a lot of movement in their particles. And the movement in the particles is limited because of the strength of the intermolecular forces. In solids, intermolecular forces dominate and it restricts the movement of the particles. Because there's not enough kinetic energy to break the intermolecular forces, the particles often just wiggle in place or maybe have slight variation in their movement, but not very much. They typically are locked into a rigid structure, often forming crystals. They'll vibrate, but not really move very much. And since they're locked in place, they cannot be compressed. And this is one of the key characteristics of solids. You can't press on them to make them any smaller. In other words, their volumes are unchangeable. But you can change the volume if you change the temperature. This is what is known as thermal expansion. When a solid is warmed up, the particles begin to vibrate more vigorously, and that actually causes space to form between the solid particles. So, when things are hot, for the most part, they increase in volume. This is what is known as thermal expansion. Now, there is a couple of small isolated situations where things don't actually expand when they heat up, they actually contract. But for the most part, solids will expand when the temperature is increased. On this next slide, we're going to talk about something called allotropes. Allotropes are different forms of solids made from the same substances. And these different types of solids may have very different physical properties. Take, for example, carbon. Carbon can be bonded to other carbon atoms in this very rigid and familiar structure. This is what diamond looks like on the microscopic level. Each carbon is bonded to carbon, to carbon, to carbon, to carbon, and it forms this structure. Diamond is known almost in all cases as being the hardest substance on Earth, and it has to do with the interlocking of the carbon atoms using covalent bonds. But what happens if some of these covalent bonds don't exist? You can still have forms of carbon, like in this case graphite. We have rings of carbon that are stacked on top of each other and held together by intermolecular forces. So this is where the intermolecular forces come into play. Not so much on diamond over here, but in graphite, we have a different form of pure carbon, but it's held together by intermolecular forces. Now there's a couple of other situations where carbon may be bonded in different structures, and these are called nanotubes, which are basically sheets of carbon that are then rolled into hollow tubes. And this can be used to make things like Kevlar. You also have graphene, which is just one very strong, flexible sheet of carbon. It's almost like graphite, but instead of multiple layers, this is one long sheet of layer. And a final one we want to talk about is this one called a buckyball, which is a soccer ball shaped looking molecule that is all carbon interlocking, and it basically forms a perfect spherical ball. These are all what are known as allotropes. Now, this isn't the only allotrope, meaning there are other allotropes of different elements, but these are just the 5 allotropes of carbon. Now, what happens when you heat up a solid so high in temperature that the kinetic energy is able to overcome the intermolecular forces holding the solid together? Well, that is what is known as the melting point. Now, the melting point is different for every solid, and it all depends on the strength of the intermolecular forces. The stronger the intermolecular forces, the higher the melting point. That seems to make sense. Ionic solids have the highest melting point of all solids because their crystal lattice network is so strong that it is very difficult to break those connections between the ions, which results in some of the highest melting points. On the other hand, molecular solids, which are dipole-dipole molecules that oftentimes are just held together by dipole-dipole intermolecular forces, have much lower melting points than ionic. Examples include sugar or even wax. Some solids that don't melt, they go straight to decomposition before reaching their melting point. Examples of this include things like wood. Have you ever noticed that wood, when it's heated, doesn't turn to a liquid before it vaporizes? It goes straight to vapor. Well, that's because the bonds that are holding the molecules together in wood are actually weaker than the intermolecular forces that are holding the solid particles together. And as a result, the heat skips the breaking of the intermolecular forces and goes straight to breaking the bonds. And so substances that don't melt decompose before reaching the melting point. It's because the chemical bonds are weaker than the intermolecular forces. We're going to finish up this video lesson discussing liquids. We'll leave gases for its own separate conversation. But liquids are basically take a solid and add a little bit of kinetic energy, and what you have is that the intermolecular forces begin to break. Not completely, but some of the intermolecular forces break. And so we have a situation where they're still held together by intermolecular forces, but there's more freedom to move, more freedom to flow, which is why we say liquids are also sometimes referred to as fluids, because the higher kinetic energy allows molecules to move past each other, but they're still attracted, so they're not locked in place. They cannot completely break free of the intermolecular forces, but there is definitely more freedom. Similar to solids, they are not compressible. You can push on a liquid, and there is still no shrinking of the volume. They stay or keep their volume. It is not compressible. Unlike gases, which have vast amounts of empty space between the particles and are compressible. So this ability to push on liquids but not compress them gives us a unique property of liquid, and this is what is known as hydraulics. Take a look at this picture down here. Let's say you have a liquid in a system kind of like this, where there's a piston that's able to push down and a piston that's able to move over here. Well, what basically happens is you fill this chamber with liquid, and when you push down on this side, the liquid, because it's not compressible but can flow, moves down and through and up the other side and causes whatever's over here to get pushed up. So this is how you can get really, really heavy things to be lifted up with very little effort using the power of hydraulics. This is how dump trucks and front loaders work. This is how even the brakes work in your automobile. When you push on the pedal, it forces some liquid down, which is known as your brake fluid, into the reservoir, and then it expands over here and pushes the brake against the tire when you're ready to slow down. Now that was an oversimplified way of showing or explaining hydraulics, but liquid's ability to move without being compressed allows for things like hydraulics to work. Well, that takes care of this video lesson on solids and liquids. Thanks for watching.